A basic calculator can add massive strings of numbers flawlessly. It executes complex mathematics instantly, and it gets the answer right every single time. Scale that up to $1 million room-sized supercomputer from the same era, and you have immense processing power at your disposal. Yet, if you asked that same supercomputer to perform a task any toddler can do, like recognizing a blurry photo of a cat in the shadows, it would have no idea what to do. This failure wasn't about a lack of raw power, it was a limitation of the instruction manual, a sign that you can't describe the visual world using only fixed binary rules. Traditional computer programs run entirely on strict human-written instructions. If this specific condition is met, then perform this exact action. That rigid logic works perfectly in highly controlled environments like traffic signals. If 30 seconds have passed, turn the light from green to yellow. Rule-based systems are effective when the world is predictable, but they become paralyzed the moment the variables start to change. To see where these rules break down, try to write a hard instruction to block a spam email. You might tell the computer to catch and block any message containing the word lottery, but a spammer can bypass that rule instantly by just swapping the letter O for a 0. You write a new rule for the 0, then they use a different word, then a different sender. Soon, you're trying to manage millions of rules that need to be updated every day, and the tricks are still evolving faster than you can write them down. The real world is too chaotic to be captured by a list of human-written rules. If a system can't find its own way to adapt to new patterns, it will always be one step behind. To solve problems this messy, programmers had to stop telling computers exactly how to look at the data. Machine learning flips the workflow. Instead of a human providing the rules to get an answer, you provide the answers first, thousands of examples, and force the machine to discover the rules for itself. Turning the logic inside out is the only way a computer can build a framework flexible enough to handle the unpredictable nature of human life. Let's apply this back to the spam problem and move past the keyword rulebook. The first step is feeding the system a massive dataset of real emails that have already been labeled by people as spam or not spam. In this 3D scatter plot, we can see the machine studying the data to find statistical correlations, hidden combinations of timestamps, sender behaviors, and formatting that humans wouldn't think to look for. When a brand new email arrives, the system doesn't check a list of keywords. It simply measures where that new message fits mathematically within the patterns it has already learned. This autonomous pattern matching is why modern filters are so much more effective than they were 15 years ago. The machine is catching subtle tricks that are impossible to program by hand. Because these systems can now identify cats and filter our inboxes, it's easy to assume they understand language and images the same way we do. But the mechanical reality is different. The system does not conceptually understand what a cat is. It interprets the image as a grid of raw numbers representing pixel values, finding statistical correlations within those numbers previously associated with the label cat. The output looks like intelligence, but the mechanism is pure, high-speed pattern matching, not conceptual comprehension. Moving from the rigidity of rules to the adaptability of learning is what allowed computers to finally function within the complexity of our daily lives. Think about your own daily work. What tasks do you perform that feel like they require deep human intuition? Are those tasks actually uniquely human? Or are they just complex patterns waiting for a machine to see enough examples?